Good afternoon. Welcome to the Embedded Executive Podcast. My name is Rich Nass. I am with Open Systems Media, more specifically with Embedded Computing Design. And my guest this week on the podcast is Mark Goranson. He is the CEO of EMASS. How you doing, Mark?
Good. How you doing today, Rich?
Just fine. Thank you very much. Before we get into the topic that I want to talk to you about, which has to do with the edge and what that actually means, let's just make sure the audience is familiar with EMASS. What do you guys do?
Okay, so we're just a small startup company. We just basically came out of stealth mode in the last couple of months. The technology's been in incubation mode since like 2020. The chip was just finished in 2025, and we're just now commercially launching the product. It's basically a very modern AI acceleration, a chip that lives basically on the very far edge of edge AI. They can't get any closer than where we operate.
Okay, that's exactly what I want to talk to you about. But why did it take you 5 years to get this chip out the door?
So it was actually in incubation mode in the in the university at Singapore, and we actually have re-engineered how AI acceleration works. We are not a typical ARM or ARM Cortex or Qualcomm Snapdragon or RISC processor only. We actually engineered it from the sensor all the way up to the output. So we actually reinvented how you do AI. We just don't bolt it onto the processor itself.
Okay, you just made this podcast go into a different direction here because this is really interesting. What do you mean by that exactly? Okay, so I, do you guys have a sensor with an engine built into it? Is that what you're referring to?
So basically, our moniker is atoms to app. And so we actually take the very far edge of AI. It doesn't matter what sensor, we can actually do digital audio, any kind of environmental inertial sensor, camera interface, you name it. We actually take that interface and it actually goes directly into an AI accelerator that's hardwired straight to the sensor. And so we do not turn on any processor until we actually activate the weight on an AI accelerator. And so that's what gives us extremely quick latency. So nobody can beat us in terms of latency or in power because we actually only turn on parts of the processor as we need to. So we have AI accelerators that are basically just on the sensor edge, listening to sensor input. And when they activate, it triggers a wait. And then that's what starts the whole AI acceleration and starts bringing up different parts of the chip. So we can actually sit in standby mode basically forever. We're down into the 10th of a milliwatt. And we
Hmm.
actually only use a couple of microjoules per inference to actually do any kind of work on the chip itself.
So are you producing these things with the sensors, or is that your customer's responsibility?
So we actually have made it easy to hook any kind of sensor up to it. We have all the sensor interfaces, but the customer actually supplies all the sensors. We have a number of proof of concepts that use a lot of different sensors to prove our case in point, but we basically can bolt on any sensor that you can imagine onto the chip.
And is this a proprietary core that you've developed?
It's actually just a RISC-V core. The core is actually pretty simple. It's basic standard. Where our IP sits is actually in our two DI or AI accelerators, as well as our AI weight decompressor. So we actually use some proprietary compression and decompression techniques on the AI model to have extremely high efficiency, but we also have a lot of really neat tricks within our accelerators that do a lot of power gating. So we basically only turn on transistors as we absolutely need to. As everybody knows, all transistors are fairly leaky, and you don't necessarily want to have all your memory operating all the time or your core processor because all of those things consume massive amounts of power. So we actually only utilize very small parts of the chip and then only use the major parts of it when we absolutely have to.
Now, most people will tell you that the really hard part of designing a system based around this technology is the software. Who does that software? Are you involved in that process with your customers?
So we actually have also engineered that to be able to be fairly simple. So we actually wanted our SDK to be a welcome mat, not a
You have
gate.
to say relatively simple when you do that because there's nothing simple when you get into AI.
Yeah, but we have made it fairly simple. We have an online portal where people can just drop their AI model right onto our chip. And so you don't even need any hardware. And we have a number of already pre-configured models that they can use. And then we actually have made it where you can use TensorFlow, PyTorch, a number of the normal tools. They actually are resident on our device, and so they can utilize all of that capability. The other thing we do have is we have the ability to take a lot of different data sets, take the data sets and actually come up with a model and port it to our chip and utilize those models. And so, people can see that real time, and then they can see the real power consumption and the real latency because, almost every company says that they're low power and low latency, but, we can actually prove it when we're under workload, right? I mean, nobody uses hardly any power when it's in standby mode. The whole key is when you're actually running AI workloads and what your power utilization there is. For instance, wake word, we only use like 3 microjoules for processing a wake word, only, 10 to 15 microjoules for processing an image. So, you can imagine that this chip can literally go for months on end. We can actually power it on harvested energy, solar cells, or coin cell batteries. So you can imagine for wearables and for applications where you want to put cameras everywhere or monitoring equipment or whatever, you can basically put this chip anywhere and power it with energy harvesting or solar cells or, small batteries.
And is it based on a single RISC-V core or is it a multi-core architecture?
So right now we just have a single RISC core, and so we actually are meant to be standalone. I mean, we can for big applications, we'll be a co-processor with other processors. So we're meant to really look for anomaly detection. And so anomaly detection means like preventative maintenance on machines or wearable rings or, security systems or crop monitoring, whatever the case may be. And so our device is actually really suited for anomaly detection on any kind of sensor.
That's really interesting. Okay, so let's go back to the original discussion about the edge and where you exist on the edge. You're talking about existing at the sensor, which I like to refer to as the endpoint.
Right.
I think that that's makes it obvious where that is. Are you also going back to the cloud as well, or are you doing everything at that endpoint?
So we do everything at the endpoint other than we can go to the cloud for if someone wants to send back data for refining the models, if they want to be able to record things for, historical reasons or whatever the case may be. So, we kind of define, like you said, we're right at the endpoint. And then there's the gateway devices like cell phones and whatnot that, we can feed information to. And then there's the whole cloud, which is, where the big guys have big AI, we can dump information to there. But for the most part, we can operate autonomously on the edge as we have, all of our SRAM, MRAM, accelerators, decompressors, the RISC-V core processor, all of that is resident on our chip itself.
MRAM. Interesting.
Yeah, so we can do either SRAM or ReRAM. And the reason why you want that is you want to have that memory always stored, right? So you can pull it up. It's typically where you want to put your weights and activations for your AI. And so that's actually stored in the ReRAM or the MRAM. And so it's, non-volatile and it stores that information. And then it can be rewritten as we refine the models or we learn more as the AI continues to get better. For instance, we actually put this on a drone modeled it, and we can actually get double the flight time on a drone because we sit between the hardware on a drone and then the mechanics. And we can look at all the airfoil, we can look at all the tilt, the rotors, the wind speed, and we can sit there and optimize that for any kind of condition, depending on the weights, the workload on the drone, the wind speed, etc. And because the AI is so quick, our latency is so great that we get to double the life out of a drone.
Very interesting. And I think you said a customer would be designing virtually through the web.
Correct. We can either have it designed virtually on the web, or we can just have it drop in the model, or a number of varieties. We have a evaluation board with the SDK we can ship to them. So we have a number of different ways where they can do the development.
And where are you in terms of having actual hardware?
So we actually have hardware today. It's actually manufactured in TSMC. Our first initial chip right now is on the 22 nanometer node, and the next chip that we come out with will be a little more efficient and even smaller, will be on the 16 nanometer node, and that'll actually tape out in the November, December of this year.
Well, thanks, Mark. This is really interesting. Like I said, this is not the direction I'd planned to take this discussion, but I think this was a lot more interesting than where I was going to go originally. So thank you very much for your time.
Thanks a lot, Rich. It was really nice talking with you, and look forward to seeing this get deployed in a lot of great applications. We're pretty excited about what all the uses are for this technology. So
Very cool. That was Mark Goranson. He is the CEO of EMASS, and I am Rich Nass with Open Systems Media.
thanks a lot, Rich.